There is such a thing as a flying pig. It's a toy. I don't have the toy, but it still makes a great physics problem. So instead of a flying pig, I have a ball on a string. So the idea of the flying pig, I can reproduce this with the string. So the idea of this flying pig is if I take this pig and it's got wings that makes it move forward, it can't fly, so it's supported by the string, and then it just flies in a circle like this. Okay, so I'm just kind of swinging this one in a circle, but the same idea. And so the question is, suppose the pig has a mass of 220 grams. I wrote that down. Suppose the length of the string is 1 meter. This is not 1 meter. And the angle between the vertical and the string is 28 degrees. Then how fast does a pig have to fly in order to move in a horizontal circle? Horizontal circle, not a vertical circle like that. That's way more complicated. Let's do it. Okay, so there's my pig. Let's go ahead and draw a force diagram for the pig. So here's my pig. I know that I have the downward gravitational force pulling on the pig, mg. I also know that what's touching the pig, well, the string's touching the pig, and the string exerts a tension in the direction of the string. So I'm going to put it like this, T. And I know that this angle is theta, right? Because if that's theta right there, that's theta too. That's your geometry trick. Now, what else is touching the pig? Yes, there is a forwards pushing force from the wings and a backwards pushing force from the drag, but let's just ignore those because they cancel anyway, and they'd be hard to draw on this picture. So that's it. In my diagram for the ball, in my example of the ball, there's no forward pushing force, right? It's just swinging on its own. Well, what's the next step? What do we always do next? We pick a coordinate system. So I need to pick my x and y axis, and I need to pick them such that the acceleration is in either the x direction or the y direction. So let's pick this as my x direction, and this is my y. Because if the pig is moving in a horizontal circle, the acceleration would be towards the center of the circle. Remember, AC is v squared over r. The c stands for centripetal, which means center pointing. So the center pointing acceleration is towards the center of the circle, which is right here in the x direction. Now I can go ahead and write my Newton's second law. F net in the y direction is equal, and I don't even know what I need to solve for, right? I do know I need to solve for v, but I don't know if I need both equations. I'm just going to write them down anyway. So in the y direction, I have a component of the tension force right here. So it's nice to draw that little right triangle, and then we can see that this side is the adjacent side of that triangle. So if I want to find the y component of tension, I would use the cosine function. So this is going to be t cosine theta. And then gravity is all in the y direction, so it's minus mg, and that's equal to 0 because the acceleration in the y direction is 0 because the pig's moving in a horizontal circle. You like that? Okay. Now let's do the x direction. F net in the x direction. There's only one force that is exerted in the x direction, and that's the component of tension. And up here you see it's the opposite side of that right triangle, so that we would use the sine function to find that. This is going to be t sine theta. So again, don't just say x component cosine, y component sine. Here's one of those cases where that's not true. Okay. And that's going to be equal to the mass times acceleration, which is v squared over r. Now, I can solve for t, right? That's not so hard. If I add mg to both sides, I get t equals mg divided by the cosine of theta. I know m, I know g, I know theta, so I know everything there. But over here, t sine theta, m, I know. I'm trying to solve for v, but I don't have r. Okay, so I need to find r. This is the length of the string. I want this distance right there. But you'll notice it's a right triangle, right? So this is the opposite side of the right triangle. That's the hypotenuse L. So this is going to be L sine theta. And that's equal to R. So let's put that in. I get m v squared over L sine theta. And I'm going to put the numbers in. Don't worry, I will put the numbers in. Now, let's, I have t sine theta, m v squared over L sine theta. Yeah. So I can solve this for t and then plug in for t. That's what I'm going to do. So I get t equals mv squared over L sine squared theta. And then I'm going to put in this for t, so it's equal to mg over cosine theta. And so we get a little weird thing here with cosine theta and sine squared theta, but I'm just going to leave it. The mass does cancel. You'll notice it doesn't depend on the mass. So I can solve this for v squared by canceling the mass, multiplying both sides by L sine squared L sine squared theta. So that's my little v squared is going to be equal to Lg sine squared theta over cosine theta. So v is going to be equal to, let's just put it up here, the square root. I can pull that L out. No, I can't. I can pull out the sine theta. But I'm not going to because I don't really care. Okay. I get Lg sine squared theta over cosine theta. Now again, let's check the units, right? So that's meters per second squared. So those two together give me meters squared per second squared. When I take the square root, I get meters per second. Sine theta is a ratio, so it has no units. It doesn't matter if you square it, it still has no units. Cosine theta is a ratio to the lengths of the sides. It has no units. Let's go ahead and put in our numbers. Square root of 1 times 9.8 sine squared 28, I wrote that weird, over cosine 28. And now let's put that in our handy dandy calculator. On drop 9.8, 28. Make sure your calculator's in degrees mode. Sine squared. Oops. Times 28 cosine divided by square root 1.56. And that's the speed. Fun problem. It's more fun if you actually have a pig. Yeah. Notice here that the tension, no, I'll just leave it. That's fine. I was going to make it like a double problem, but I think it's good. Okay, the end. Flying pig.